Everyone, welcome back to another lesson in MTH1W. Today we'll be looking at number sets. The idea of grouping and classification is how numbers were developed. Historically, numbers were developed starting from the most specific subsets. With time, civilizations needed to work backwards, creating bigger, more encompassing number sets. For example, at the very beginning of civilization, there was a need to count objects, creating the natural number system. Later, people need a number to represent having nothing. So zero was created. Then people began to barter and trade, so the concept of owing someone items, led to the creation of negative numbers. This greater need for classification of numbers created our number sets and subsets that we know today. In fact, real numbers are not the only types of values used in mathematics today. There's a larger number set called complex numbers, which includes a subset called imaginary numbers. So here we have a diagram that represents the different number systems that are represented. There's real numbers, rational numbers, integers, whole numbers, natural numbers, and irrational numbers. When we look at real numbers are all the numbers found in a number line. Some examples that we can have are negative 100, negative 0.5, 0, negative 3 over 4, and pi. So real numbers encompass every type of number. So it encompasses rational, integers, whole numbers, natural numbers, and irrational numbers. So the first subset we'll look at here is what we call rational numbers. Rational numbers are all the numbers that can be written in the form a over c, can be written as a fraction, where a and c are integers and c cannot be equal to 0. So some examples here we have are 1 over 2, negative 7, 127 over 300, and negative 3 and 1 over 4. Anytime you see something that has a repeating decimal, or a decimal that will terminate, this would fall into the category of rational numbers. So here, if we look at our examples, something like 1 over 2 would be considered a terminating decimal because, again, 1 over 2 is equal to 0.5, which means that it stops. A repeating decimal, again, is represented by something that has a line on top of the number. So, for example, something like 1 over 3 is what we would consider a repeating decimal because we get an answer of 0.3 repeating. So the line again represents the repeating here as well. The next subset we'll look at is what we call integers. Integers are numbers whose numerators can be divided evenly by their denominators. So an example here would be negative 100, 0, and negative 8. The next subset is what we call whole numbers. Whole numbers are the set of integer values greater than or equal to 0. So here some examples are 0, 1, 2, 3, and so on and so forth. Natural numbers are the set of integer values that are greater than 0. So here, when we look at the difference between whole numbers and natural numbers and whole numbers are integer values, but natural numbers do not include 0. So for example, 1, 2, 3, 4, so on and so forth. When we look at real numbers, again, they're split up into two subsets. So we looked at rational numbers and the corresponding subsets, but they also have what we call irrational numbers. Irrational numbers are the numbers that cannot be written in the form a over c. these numbers are non-repeating, non-terminating decimals. So we already looked at, again, what it means by a repeating decimal or a terminating decimal. And so these are irrational numbers. So something like pi and square root 2 would what we call irrational numbers. So here, when we look at a number line, so here if we look at natural numbers, remember natural numbers are the set of integer values that are greater than 0. So if we're going to represent them on the number line, that would be 1, 2, 3, 4, 5, 6, 7. Those would represent the natural numbers on this number line. Whole numbers are the same as the natural numbers, but also include 0. So here we'll do all the natural numbers, but also including 0. And then real numbers encompass every single point on this number line and all the values that are in between as well. So here we can draw it as a line that encompasses the entire number line and goes from here, -6 to +7. Here in this example, it says identify the number systems in which each of the following numbers belong by marking the columns. So here we have +7. So here if we start from the right, again, pretty much all numbers are going to be real numbers, unless it would be an imaginary number, which we're not going to talk about here. But again, here, 7 is a real number. It's not an irrational number because we can write 7 as a fraction. We can write it as 7/1. So therefore, it's going to be a rational number, an integer, a whole number, and a natural number. Here, -3/4, we see that's going to be a real number. But here, it's going to be a rational number because here, again, it's written as a fraction. So not irrational, but rational. If we look at pi, that was one of the examples we used before. It's a real number, and it's also a rational number because it's not a repeating decimal or a terminating decimal. And finally here we have -√81. So here we may be tempted to say that it has a square root, so automatically we might say that it is an irrational number. But here if we actually square root 81, that gives us +9. And then here there's a negative at the front. So our answer here of -√81 would be -9. So -9 would be a real number, a rational number, and also an integer. The next example here is telling us to graph each of the following on a number line. So here we have 3 and 1/2. So 3 and 1/2 would be 3.5. So again, that's going to be between 3 and 4. So here we can write 3 and 1/2. The next one is -4.8. So that would be between -4 and -5, but it'll be closer to -5. And so here we can write -4.8. Next is square root 30. And square root 30 is equal, if we calculate that, approximately 5.47722. And so square root 30 will be between 5 and 6. And we can put that point there on the number line. And so D here says all the natural numbers greater than equal to -3. So again, all the natural numbers greater than equal to -3. Here, remember, if we look at our definition of natural numbers, remember natural numbers are the set of integer values greater than 0. So even though it says here that it's greater than equal to -3, we're going to ignore -3, -2, -1, and 0, because those would not fall into the definition of natural numbers. So rather, we see here that if we put on the number line, all the natural numbers that are greater than or equal to -3, here would start 1, 2, 3, 4, 5, 6, and 7. And next here, it says all the real numbers less than or equal to 0. And so here, this is what we call set notation. So this is written in what we call set notation. And so the XER, this is saying that X is an element of real numbers. So this is saying X is an element of real numbers. But there's a condition here as well. And the condition is that X is less than or equal to 0. So again, this is written in set notation, and X is an element of real numbers, but the condition is that X has to be less than or equal to 0. So here it starts at 0, and it moves to the left. And it encompasses all the real numbers, so we can draw that with a line. The next one is all the real numbers less than 0. So again, it seems like the same question, but the first one was less than or equal to 0, and this one is just less than 0. So the difference here is how we represent the point at 0. So initially we represented the point at 0 with a closed circle, but if it's just less than and not less than or equal to, we're going to represent that with an open circle. And so here we see that open circle means that it's not including, so does not include. But here, a closed circle would mean that it includes the point. Okay, so here again, in the first part, X is less than or equal to 0. We represent that with a closed circle. In the second part, again, less than 0, open circle means it does not include. Okay, moving on to number sets and subsets. So here, a set is a collection of things with a common property. Each item listed within a set is called an element of a set. We write sets using set notation as we just explored. So the set of whole numbers that are less than or equal to 8 is represented by, again, these brackets, and within the brackets represents the set. And so we have the elements 0, 1, 2, 3, 4, 5, 6, 7, 8. If we were looking at the set of natural numbers that are less than 11, so the set of natural numbers that are less than 11. So natural numbers, again, integer values that are greater than 0. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And here we're not including 11 because it is less than 11. Next is the set of integers that are less than 0. So integers that are less than 0, again, would be -1, -2, -3, and then so on and so forth. And so here, subsets are smaller sets that are made up from larger sets. Subsets can have anywhere from 0 to infinite elements. And so example here is given the set of whole numbers that are less than or equal to 8, which we see above here. Create a subset that includes prime numbers. Remember, prime numbers are numbers that can be divided by themselves and divided by 1. So remember, prime numbers are numbers that can only be divided by themselves and divided by 1. Remember, prime numbers are numbers that can be evenly divided by either themselves or by 1. And so the prime numbers in this set would be 2, 3, 5, and 7. If it includes all the odd numbers in this set, that'd be 1, 3, 5, and 7. And here it has 4 elements, so we can pick any 4 values there. So we'll just pick 1, 4, 6, and 8. So these are any 4 elements. And then if it has no elements, we just represent it by the 2 brackets with no elements in between. And this is what we would call a null set.